Okay, this is going to be the differential equations lesson for section 2.1 on slope fields and phase portraits. Chapter 2 in general is going to be when we're going to start learning methods for actually finding the family of solutions. We'll start that in the very next section, 2.2. So this is the last of the kind of general overview kind of topics before we get into the meat of how is it that we actually find these solution functions. But this is an important one to understand, especially this first part. So whenever we have, and by the way, chapter 2 is going to be dealing just with first order derivatives. Now that we've kind of established things, we're going to deal with what we can do with first order differential equations first. And then in later chapters, we'll deal with what's called higher order. We'll see it here and there, but mostly this is going to be about what we call first order differential equations, which means that first derivative will be the highest derivative that appears in the differential equation. All right. All right, so in this first section, we're going to consider first order differential equations and just equations that are of this particular form if they can be solved for their derivative. So if I have the derivative on the left, dy dx, or any or dependent and independent variable is some function of both variables on the right, okay? So if I have a differential equation like this, then that means that any solution to that will be an equation of the form y is some function of x, right? Since we already used f here, our book likes to use phi here for this, but it's just y is some function of x, okay? So here's the idea. If you were to plug different points in, like let's say I wanted to go to a particular point here, like 1, 2, okay? So this is the point 1, 2 in the domain. If I plug that point 1, 2 in over here, I'm going to evaluate this to a number. Maybe this number turns out to be 3, okay? Well, that 3 will therefore be the slope of the solution curve at that xy, right? So this 3 is a slope at that place, right? And so the solution curve would have a slope of 3 in that region, okay? So often what we do with differential equations is we produce something called a slope field or a direction field. So it's a graph that looks like this, where at various places in the xy, we've plugged in the xy into the right-hand side and figured out what the slope would be, because the derivative is the slope. And then we put just a little piece of the solution curve there. These are little line segments. Sometimes they're referred to as lineal elements, but you can think of them as just a little piece of a solution curve at that point, right? So it gives you an idea of the behavior of the solution curve across the domain for a particular derivative, because the derivative is defining the slope at different xy's, okay? All right, that means that different solution curves will end up following the flow of the slope field line elements, right? And then if we wanted to know a particular solution curve, we'd have to know the initial condition. If the initial condition was this point, then it would be the solution curve that kind of builds into and eventually flows through that point. If the initial condition was this, it would be this one, or maybe we had to go through this point here, which would be this right here. So it's going to be a particular solution curve that's flowing along the slope field, but going through a specified initial condition point. All right. All right. So one thing we might be asked to do is to sketch these slope fields. So to sketch a slope field, you just pick a bunch of xy values in the domain, plug them into the right-hand side, and then draw little linear elements that show a little piece of a line slope at that point, right? So for example, let's say that I took this point 1, -2. So I would plug in 1 for all x's and -2 here. And so I would end up with -1. That's how I got this number. And that means that if I go to 1 in the x and -2 in the y, I have to do something that has a slope of -1 for every one, right? So I just drill a little line with -1 slope here. And you would do that for a bunch of different elements here, right? So that's for this equation here, okay? And this particular equation had y as the dependent variable and x as the independent variable, right? So I drew an xy plane. Okay, here's another one. This one is dp dt equals p times 2 minus p. Okay, so the dependent variable here is p and the independent variable is t, right? If you do that same kind of a plot, you can check this and pause the video and try a few of these points yourself if you want. You would end up having slopes that look like this. And actually, this function, the slope field, looks a little different than this one, right? So this suggests another way to classify differential equations based on the appearance of their slope fields. And what's unique about this is that if you look as you move in the t direction in the independent variable direction, there's no change in the slopes. The slopes are constant at for all t. Once you get to, I mean, it depends on p, right? But it doesn't depend on t. It depends on the y variable, but not on the x variable. This one seems to depend on both. And the reason is because this function out here contains both the dependent and the independent variables, right? Whereas this one contains only the dependent variable and no independent variable. Therefore, it doesn't depend on the independent variable. So whenever you have a first order differential equation where the right-hand side contains no x variable or the equivalent, that's referred to as an autonomous differential equation. And one that contains both and therefore has dependency in both directions is called a non-autonomous differential equation. Okay, so that's another classification technique, okay? And for autonomous differential equations, there's another kind of graph that we can produce called a phase portrait. Okay, so many ordinary differential equations in the real world are autonomous because a lot of times the independent variable is time, right? But it's not true that the derivative of some quantity with respect to time always depends on time. It could depend on something else like populations, right? The rate of change of a population might depend on the size of the population, but not on the time itself, right? Or the change in temperature over time might depend upon a differential temperature, but not on time, right? Or some other quantity. So all of these things have the property that lowercase t does not appear in the right-hand side. So the slope doesn't depend on the quote x variable, the time variable in this case. All right. Okay. So whenever we have some autonomous differential equation where the right-hand side contains no independent variable, then you can solve that right-hand side equation for places in the dependent variable that would make that right-hand side zero. And those are called critical points, okay? And they are interesting because they result in what's called equilibrium or constant solutions. So if I had this equation here, which was the example before, since p times 2 minus p is 0 when p is 0 or p is 2, if you look at the slope field, notice what's happening at those values. Those are places where the slope is 0, right? And therefore horizontal. So at the critical points, we have constant solutions. The slope is just 0, okay? But what happens near those values is that they divide this dependent variable into regions, right? So split at 2 and at 0. And if we just look at the region between the two, the slope, for any p that we chose in here, the slope would always be positive. It's 0 here and it's 0 here. And then on the other side of this critical point boundary, the slope becomes negative. All the slopes are negative down here, right? For different p-values, different negative values, but there's no positives until we encounter another critical point. So the critical points divide the dependent variable into regions where the slope goes from being minus to positive to minus. Okay, not necessarily that, but it can only change at these places. The slope is 0 right at the critical points. Right, so what we can do is we can just draw just the y-axis here, just the dependent axis, mark the places of any critical values, 0 and 2, and then just put an arrow, and the arrow goes downward if the slope is negative, and it goes upward if the slope is positive. And that picture has a name. It's called a one-dimensional phase portrait or a phase line. So you may be asked to draw phase lines or phase portraits, and that's what's going on. If you have an autonomous DE where things are not dependent upon the x variable, then wherever the x variable is 0, right, the slopes are downward or upward or downward. And so you just draw that as a phase portrait line. You just say, okay, at 0 and at 2, they go down here and they go up here, the slopes. Okay, that's called the phase portrait. All right. And then let's talk a little bit more about these critical points themselves. If you look at what's happening to the solution curves, like these green solution curves I've drawn here, they will tend to have negative slope for a while until they get really close, and then they kind of get very close to having a 0 slope. Same thing here. We would have a positive slope that starts out close to 0 and gets more positive and then becomes less positive as it gets closer to 0. So the critical points, if you look at the solution curves, they form asymptotes, right? The solution curves will have asymptotic behavior as they approach the critical points, right? All right. They will tend to align themselves with that. Okay, which is why these are called equilibrium solutions, because or constant solutions, because once we get close to a critical point, then the solution tends to be stable at that region. Okay. All right. And as a result, there are special names for these critical points themselves. If you have a critical point where the slope is going down from above and up from below, where the solution curves would be approaching this, then this critical point is called a stable point, and it's also called an attractor because it's attracting the solution curves to itself. Okay. On the other hand, this critical point at 0 here, right, the slopes are positive on above and negative away, which forces the solution lines away from this. And therefore, this critical point is called an unstable critical point, and it's also known as a repeller because it repels the solution curves. The only other possibilities would be if you have a critical point, and this is possible to have, where the slopes are positive on this side and positive on this side, or they're negative on this side and negative on this side, they don't change sign, then we call that those critical points semi-stable. They neither attract nor repel, and it's not stable the way this is. Like the solution will not stably orient there. There's just an unusual thing happening here, right? So those points are labeled semi-stable. Okay, and then the last topic is, if you remember back in Calc 3 when we studied multivariable functions, sometimes we chose a particular output value, and then we drew all the curves in the domain that produced that output value. Those were called level curves, kind of like a topographical map, right? For different altitudes, we have like a line that represents all the places that are at 5,000 feet or something like that. So we have something similar for differential equations. They're called isoclines, but they have to do with different places in the domain that have a constant slope value, okay? And then we can sketch that. So for example, let's say I have this differential equation here, and I wanted to find all the places that have the slope positive 2. Well, you could just replace this with positive 2 and then solve for this curve, right? That would be x, y plus x equals 2. You could factor in x out and get x, y plus 1 equals 2. Therefore, y plus 1 is 2 over x. Therefore, y is 2x over 1. And if you graph that, it produces this blue curve, right? It's got two legs to the curve here, but every xy value that's on this value has a slope of 2, right? Its slope value would be 2 all the way along that, okay? On the other hand, if I wanted to pick a different value like 4, like where are the xy places that have a slope of 4, I could put a 4 there and I would get y as 4x minus 1, which is these curves. These are the places where the slope is steeper. At every place on there, the slope would be 4. Okay, so drawing something like a level curve, but levels of the slope for the differential equation is referred to as an isocline. Okay, lots and lots of terminology, especially here in the beginning of the course. And that's all we're going to do with 2.1. Mainly, we're going to just work with slope fields. Starting in 2.2, next week, we will begin learning our first techniques, starting with the first one, which is called separable variables. So you should have enough at this point to do the 2.1 homework.